Hello everyone, and I would like to thank my Armenian colleagues for inviting me here. It's always a pleasure to give a talk in Armenia, and especially I think that today I've heard a lot of very interesting and insightful questions from the audience, and so I decided that I will try to leave enough space for your question and discussion in my talk as well. And today I will talk about large language models, and I will try not to go into many details, but give probably my subjective overview and conceptual understanding where we are today with large language models. So my talk is titled Promises and Failures of Large Language Models, so I will try to show what is good and what is not very good with them. And I would like to start with the question, can we achieve AGI by learning the next word prediction only? So probably you have already your own opinion on that, or maybe you would like to think a couple of seconds, and I would like to ask you to vote. What do you think about this? So can we achieve AGI by learning the next word prediction only? So I would like people who are thinking that we can, so the answer is yes. Please raise your hand.
It should be not more.
Yes, so then people who think that we cannot achieve AGI by learning the next word prediction only. Yeah, I think that at the moment, probably we should repeat this after my presentation to see if this will change. But now we have like probably twice more people thinking that it's not possible to achieve AGI with the next word prediction only. And actually, why we are talking about the next word prediction, why it's important. Actually, it's in the heart of language modeling. So what we have as a language modeling, we have some initial string which we try to autoregressively continue with our generative model. And why people started doing this? It's in some sense it seems stupid, because before that we have machine learning approaches where we have a lot of labeled data. So you have examples how to solve tasks, and you train your model to solve particular task. But here, we are not solving any particular task. We're just predicting the next element in the sequence, the next word, how it might be useful. Indeed, it has some very interesting properties, this next token prediction task. For example, if we look at what is happening in animal brains, we will see that during their behavior, they are constantly predicting what will happen next. So in some sense, we see that first we can observe that in nature, intelligence and adaptive behavior is connected to the prediction of future events. And on the other hand, you can easily explain why it's important in biology, why it's important in evolution. Because the better you can predict your environment, the better you can survive, because you will be prepared and you can adjust your behavior to that, which actually it's some biological analogy. But then we can propose what I call here like a text world corresponding hypothesis. We can say that, okay, if we have all the texts produced by humanity, then probably certainly they reflect in some sense what is happening in environment. And then if we will try to train model which will optimally predict next token of the text, then for this prediction, the best way to do this, the most optimal way to do this, is to distill some kind of world model, like representation of the world from the text, and use this world model to predict next token. So it's much better than to memorize all possible continuations of the text, because you can have a more or less compact model which you can recreate from the all available texts, and then you just condition on this model on predicting what will happen in the world, and given that, after you can decode it into the textual continuation. So this is, I think it's like a foundational hypothesis which is related to this question of can we achieve AGI with only the next token prediction. So if this hypothesis is true, then possibly we can do this. So if LLMs really distills this world model, and during distilling they also learn how to reason with this world model, then probably we can achieve AGI. So this is why sequence prediction is so important conceptually. And it leads, as I've already said, to some kind of paradigm shift in machine learning. So before that, we have a task-specific learning, and after that, we have more universal problem solver. So the question you can ask how, now it's obvious to almost everyone, but say 5 years ago or 7 years ago, it was not obvious how we can do this. So here, just some short detour into the history. If we take GPT-3 and look at these experiments, what we will see, so with LLMs, you will be able to set your machine learning problem not as a task of learning this set of examples and correct labels, or these input descriptions of the problem and solutions, so trying to predict solutions from some problem statement, but as a task of giving description of the problem in natural language, and then asking your model to continue to generate solution, and hoping that if you train it on the all possible description, like all the human knowledge, it will be able to find solution just by generating it. So what initial experiments with the GPT-3 showed us? So if we look at this machine translation accuracy here, experiments. So if we, here on the x-axis, we have a number of examples in context of our model. And certainly, if you just given instruction and no examples, you have pretty modest results on prediction. Even so, here we consider 3 different models, like 1 billion, 13 billion, and 175 billion parameters. And even with 100 billion parameters, it's still 20% accuracy. But if you add one example, you see this jump in quality of your prediction. And if you add more, you have even better results, and it scales with the model size. So then the question is, if this performance due to ability of larger model to actually distill some kind of world model from the texts and use it, or if it's due to just memory capacity. We can say that here LLM just has more parameters, so it can memorize more. So it has no world model, it just has some dump of all probabilistic, it's like probabilistic information retrieval system which generates the most probable answer, retrieves probabilistically what was observed during training. So let's try to consider these two hypotheses. And actually, even without thinking about what are underlying mechanisms of performance of large language models, we can see that people starting from 2020 tried a lot to train large language models. But you see, we have had a lot of models here, but the most important one, ChatGPT, emerged only after, here it's like about 3 years after these progress and this explosion of LLM started. And why now all this is mainly irrelevant for us, and we are actually discussing and talking about all these models. Because before that, even if we have trained large language models, their text prediction was too general or too unspecific to be helpful for our application. So why is that? Actually, it's embedded in the nature of text generation by transformer architecture, which is in the heart of large language models, because it's like some probabilistic algorithm, and this is why LLMs sometimes called stochastic parrots. And then when you predict every next element of your sequence, every next token or word with some specific probability, and as you can see in this example, we have this as our prompt, and you have like two steps like two alternative steps to decode sequence. And you can see here, for example, if you follow this higher step and you always sample highly probable transitions, you will have one result which has a full probability like this. And probably if you sample another sequence which has a smaller probability on the first step but larger probability on the second step, you will have high overall probability for this case. Which means that if you have, when you when you query, condition, and try to generate text with the LLM trained on all the text of the internet, you will have something like a mixture. Your model switches from different, imagine that your model, it has a lot of different alternative ways to decode your initial sequence. And then, probably for you, you want model to select only one of the options and continue it. But the model is just mixing all these options on every step. So this is why we have these wide hallucinations. And ChatGPT was the first example of very successful using of reinforcement learning to fight this problem. Because during reinforcement learning with human feedback, you select and you reinforce not individual tokens, but all the tokens which constitute a helpful and useful answer in some particular domain. So what OpenAI did, they say that let's take a general purpose LLM and then try to fit it for particular purpose to be helpful for some human user to solve its tasks. So how RLHF works? So first it starts again with a normal supervised fine-tuning, where you provide models with examples of useful, helpful behavior created by human users. So it is now not just texts describing something. It's a particular like explanations or instructions how to solve some tasks. And then we try to increase probabilities of answers which will be helpful. After that, we want to generate more data for our next step, like further increasing probabilities of the useful answers. For that, we use these pre-trained models to generate a lot of examples of responses for user prompts, and then annotate them with a human user, like rank them with their usefulness, and then train reward model. And actually, this is also very important step because before that, before instruction tuning, for example, as I'm like working with a conversational AI system starting from 2015, one of the most like pressing problem in conversational AI was absence of good automatic evaluation metrics. So this is one of the solutions. So you can train a model which says that some particular type of answers is good for some particular task. In this case, it's being helpful for solving user problem. And after that, you like train your model with the RL and with this reward model to produce correct answer. So then, if we're now trying to summarize what has happened with the machine learning during, say, last 10 years, we can see that first we started with this picture when we had a lot of like task-specific data sets, not very large. And we trained like specific models for specific data sets. After that, and it was like very specialized in domain models. After that, we started to train like more universal models, and we know this as a knowledge transfer. So for example, the first model of this type in natural language processing was BERT, when we used masked language model objective to train some model which has very good representation of the natural language. And after that, we can fine-tune it with much less data. And even with much less data, for specific tasks, we can achieve much better quality. So then we have like two stages: train, unsupervised, like self-supervised model on the like denoising, like prediction of blank parts of the text model, and then fine-tune it for tasks. And LLMs, they pushed this even further. Like we train a model which is universal for any task. So we don't need this fine-tuning in the limit. And here it's like fully supervised trained. And because in our texts, in descriptions, we have examples of solving problems, this model, we will just give description of the model of the problem to this model, and it will solve it by itself. And so what we have seen after we observed this like very efficient training, and how we can measure progress of LLMs, how we can understand if they are becoming more and more intelligent. And one of the most popular tests is this MMLU, which is basically you have a lot of in-domain questions in different subjects, and with answers, which is solved by students, and then you can like test depth of knowledge, or some, you can say, common sense or understanding of the world of your LLM. And you see here that like we have a pretty, starting from 2020, pretty fast increase in the quality of the models. And when this data set was published for the first time, actually GPT-3, as you can see here, was not like the leading model in solving this task. It was better solved by specialized model unified QA. But then, now you see that GPT-4 and, I don't know, what is it, probably some Gemini, it has like pretty high knowledge of all these subjects. And it's like pretty impressive. It's, I think today no one will say that average human is much better than GPT-4 at answering this type of questions. But of course, if we are thinking about intelligence, maybe just memorizing all the correct answers from different textbooks is not good enough. Probably we need some creativity to solve complex tasks. Sure, we need. And here is people started to test, to apply creativity tests which were developed for humans to test creative capabilities of LLMs. And they found that, I was pretty amazed when I've seen this. So there is some test for creativity, which is called Torrance test of creative thinking. And it's pretty popular in US. And there are tens of thousands data points how students in US answer these Torrance tests of creative thinking. And what was done in this paper, researchers take a control group of students and GPT-4. And this Torrance test of creative thinking, it has like a visual part and verbal part. They concentrated on only on the verbal part. And you can see actually that this control group, it has like much worse performance compared to GPT-4. GPT-4 is like in top 1% for originality and fluency, top 1 percentile of national results in US, and in flexibility like top 3%, compared to like about 60% by the control group. Which means that compared to the average student, GPT-4 is much more creative. If we believe that this test is really testing creativity. Yeah, great. You see, we trained model for next token prediction, and it's so creative. We can add. It's very cool that we can, on top of LLM, we can add so many different cognitive skills. In some sense, I feel that right now we are in the golden era of old-fashioned symbolic AI, because all these tricks, all these cognitive heuristics like chain of thought or selecting hypothesis, it was very popular in symbolic AI before that. But symbolic AI missed this like fuzziness and semantic understanding of the LLMs. But now you can easily, without any coding skills, just try to experiment with the different cognitive architectures like chain of thought to improve your results. And the question is here, so what is chain of thought? The simplest example here is that you provide in a prompt not only examples how to solve problem, like a question and solution, but also intermediate steps how to solve this. And one explanation might be that when you provide all these intermediate steps, it allows models better learn. Like we've seen emergence of term in context learning, which I hated so much after I spent a lot of time in machine learning. For me, like learning is something which changes parameters of the neural network. So in context learning is feels like some nonsense. But still, people say that we have in context learning. And if we gave more example with an intermediate steps, this will allow our large language models to learn how to solve the problem. Because here, like LLM should invent how to solve the problem itself, and here it can learn from examples. So this is why solution is much better. On the other hand, some critics might say that, no, actually your LLM is not learning how to solve the problem. It's just better conditioned, and it gives you examples how to split generation on the shorter parts, and for the smaller chunks you have high certainty, and then your error is not accumulated so far. So here you just better condition your model for generation. It's not a learning. Yeah, and certainly people invented a lot of architectures. As I've said, it's like a Nero plus old school AI, where you have like this basic chain of thought, you have a sampling-based chain of thought, verification-based chain of thought, tree of thought, and graph of thought. And all of these you can experiment with, and probably you will get better results, but we are not know yet why you get better results. We need to study this. And why we still don't know. We will see a bit later. Another problem, so great. We have very good flexibility at implementing different cognitive strategy, how we can teach our LLM to learn. But actually, in some sense, we are limited by the input context size. So if we have some complex problem involving analyzing long documents, or description of our problem is very long, maybe we have not enough capacity in our model, in input of our model, to generate an answer. And so people started to invent a lot of stuff, and basically the most obvious is that given that we already have all these semantic search engines, so all this information retrieval stuff, it's already used in Google, Yandex, all these search engines when we try to retrieve texts by semantic similarity to the queries. We can reuse the same models to build some sort of semantic search for all the documents which are relevant to our problem. And then we can query this database, so like extract some important information which is useful for our task, and then put it in the context and generate solutions. So it seems like straightforward solution. Great, now we can like use almostly infinite knowledge, and which is also most important. This is like evolving knowledge. So if new knowledge is created, you don't need to retrain your model. You just need to add this new knowledge into your vector database. And these like get a name of retrieval augmented generation. Yes, cool, but can we go even cooler? Certainly. So what we had in our old-fashioned machine learning, we had this thing that human teaches AI to do something. But after we got this ChatGPT thing, what we did, it's like, now junior programmer is like the most important skill is copy-pasting from ChatGPT. So, but it's stupidly, yeah, you see that you have some instruction and then you execute it. The question is, why do we need human here? Why we can't just take this instruction and execute it by another model? And here come agents. So we're removing human from the loop and say that now we would like to have a fully autonomous system which generates plan how to solve some problem and then solves this problem by itself. Yeah, very cool. Let's consider like a very basic general architecture of autonomous AI agent. So we have some agent which is usually has some LLM inside it, some LLM engine with specific prompts, and you have some set of tools, and you want your agent to call these tools with some particular arguments, so to execute some functions. So the agent given problem can like analyze which one of these tools is needed, given short-term memory, like current context, and long-term memory, probably something retrieved from the vector database, to generate then like to have available actions, then do planning and executing a plan, then have some these fancy cognitive stuff like reflection, self-critics, chain of thought, sub-goal decomposition, all this stuff which you need to have a proper plan and then analyze what you have did. Did you something wrong or did you something sufficient to achieve your goals? Yeah, very cool. And now people gone crazy. You see now we can remove human from the loop. We can create digital workforce. It's like our dreams comes true. Yeah, we can go fishing now, and everything will be solved. Yeah, actually, I'm so amazed that during last like 2-3 years we are living in a wonderful time when we have so many optimism, and every year we have new developments. Yeah, that's really cool. And for example, this is an example of agent architecture. So usually in many autonomous agents, they are not learning in specific domain. They use their memory, which is already collected to solve some problems. And with my colleagues from AIRI Institute, we have proposed some knowledge graph-based agent architecture, where agent interacts with the environment without any prior knowledge about this specific domain. In our case, we selected some text-based games, and then during this interaction, the agent learns by building some knowledge graph describing this world, so like exactly trying to build world model in the as a knowledge graph, and as well as by adding to this knowledge graph not only some semantic links, but also links to episodic memory, which is related to the facts written to this knowledge graph. And we found actually that if we use this technique to learn environment with the knowledge graph, we can do much better than if we will just put all the history of interactions between our agent and environment in the prompt, or if we use retrieval augmented generation to retrieve relevant memories, or if we just summarize all the history into the prompt, we are way more better and we will be able to solve much more games than in this case. And we even better than not very engaged human user, but not as good as a human which is very interested in playing this game. So, yeah. As we learned from the first part of the talk, LLMs have knowledge, reasoning, creativity, and autonomy. So the question is, can they survive in the wild? By the way, probably we need to revote our question. Like, we had a lot of optimistic stuff now, so let's try once again. Do you think that next token prediction only is sufficient to get to AGI? Who is thinking that the answer is yes? Please raise your hand. Yeah, almost the same. I was not very. It seems that I was not very efficient at pursuing this. That LLMs can solve everything. Okay, can they survive in the wild? So, what comes to your mind if you have idea of autonomous agents? Certainly, it's some web agent. So you have a lot of websites and a lot of tasks, or you have a computer interface, and you can create a good like simulators for these environments, or you can collect a lot of data, which will help you to test your agents in these environments via API. So you can take a look then at something like Agent Bench, where you have these challenges, environments, and then you can like plug in your favorite architecture and try to see what will happen. And what will happen, I will not dive into details of what are these tasks, but actually this success rate is not probably is not pretty useful for practical applications, because if you have success rate like 30% or even 60%, not so many applications when it's tolerable for you. Yes, very disappointing. So why this might be disappointing? We don't know exactly, but we have some hints from the study. From the results of the study, I will tell you right now. So what we're considering here, what is the question I'm trying to find answer for myself? Is large language model, is it as a large world model, as we described at the beginning, as we discussed at the beginning of our talk? Is that model tries to learn world model from the textual data, and to use this world model it should learn also to reason on top of this world model, which means that LLM has some internal ability for reasoning and for abstracting algorithms of problem solving from the textual description of the problem. And or LLM is LISM, or which can be which is acronym for large idiot savant. And idiot savant, it's a condition, it's a human condition when we know that some humans, they are very good at remembering something, so they can remember almost everything, but they cannot reason. So this is why they are called idiots. So let's try to differentiate between these two options. And we will try to do this with this problem, with this task, which is called blocks world. So you have a tabletop and you have some cubes on the tabletop, and you have, say you have like these cubes, and you have initial state, and you have a goal state, and you need to create a plan how to go from initial state to the goal state by picking up individual cubes and stacking them on top of each other. So the question is, how good is large language model, like how good ChatGPT can solve this problem? So let's try to estimate your expectation. I suggest to raise hand those of you who think that ChatGPT can solve more than 50% of problems in this domain. More than 50%. Okay.
Does the accuracy matter?
Huh?
Does the accuracy matter?
Yeah, you can only solve this problem or not, if your plan is correct or not. So the question is if ChatGPT can solve more than half of the problems.
But always for problems, right?
Probably, I'm not sure. Maybe 6. Not that much. Yeah. Less than 50.
I think 30%.
30%.
Less than 10.
Less than 10. Have you read the paper?
No.
So actually, GPT-4 has 34%. And interestingly, if you add chain of thought reasoning, you will not get much better with that. Just 35.6%. But then we have another interesting option. What we can do, we can try to understand if our model just remembering something similar to this block worlds problem and try to reuse these parts to build most probable plan, or it's really understand the planning problem. So how we can test it? We can try to reformulate this description of the problem just in another term. So the planning problem is the same, but we just give different names to the objects and to the actions. Here in this case, we obfuscate the action names, like pick up becomes attack, unstack becomes feast, and table becomes planet, hand empty becomes harmony. But So we just reformulate problem, leaving the same. If you read description, you can actually, if you abstract algorithm of solving this problem, you can solve it. Now you can see this is called mystery block vault. You see it's now GPT-4 one shot can solve it like 2.6. Chain of thought actually works here much better. It can solve it in almost in 9% of cases. Yeah, and surely if we just use random alphanumeric names for action and object names, we will have 2% one-shot accuracy. So how we can interpret these results? Yeah, it seems that LLM is more like large idiot 7 than the large world model. We don't know. Probably yes. Actually, before I've seen this paper, I was a believer in the first variant. But after I've seen this result, I started to doubt that actually LLM can build a world model, given this current training procedure. Okay, let's go further. How good are LLMs at memory demanding tasks? So consider this task. Here you have some facts scattered along the text, and you have a question. The question is, where was the football before the bathroom? Yeah, it's hard to answer this question, given the text very quickly. So let me help you. So I will highlight facts which are relevant to this question. And you need 3 facts to answer this question. So Sandra traveled to the office, Sandra picked up the football here, and Sandra journeyed to the garden, Sandra journeyed to the bathroom. So what is the answer? There was the football before the bathroom. Huh? Garden. Office. Office or garden? It's very hard task even for human. Garden. Okay. As we worked on the extension of the context, we decided to build data set to test long context capabilities of current large language models. So what we did, we took a lot of books, and we took a very well-known data set, which is called baby data set, proposed by, maybe all of you knows Tomasz Mikhail and Burtsev, and he was one of the guys who proposed this baby data set with these simple facts like Mary went to the bathroom, John moved to the hallway, Mary traveled to the office, where is Mary? So you can procedurally, algorithmically generate a lot of facts and correct answers and questions. And these facts, they are not common knowledge. So it's like a leakage-proof data set, because LLMs cannot learn these facts. They can only find them in some text. And then we take these facts and then just randomly pick up some places in books and between 2 sentences and place these facts inside books. And we had a nice setup where we can add as much background text as we want, uniformly distributing these facts inside the text. And we have tasks of different complexity which tests reasoning of LLMs. So let's look on our initial results. So if we take the first task from our data set, which is single supporting fact, which means that you need only 1 fact. So probably you have 3 facts as here, but you only need 1 fact to correctly answer the question. And you test different LLMs like GPT-4, Phi3, Mixtral, Llama on different context lengths. The first points here are just facts without any background text. So you can see that all LLMs we included in our benchmarking would have very good results here. But as we add like 1,000 tokens, you can see that GPT-4 is still very good, but some other models, their performance drops. Then you have 10,000 tokens. Then, well, for 10,000 tokens, only GPT-4 has performance better than 85%. And probably, if you want to use your system in production, and you have some important facts for your user, and you want to have reasoning and give a correct answer, like performance below 85 may be not good for you, which means that probably even like GPT-4 after 16K is not useful for you. Yeah, pretty interesting results. Even for single fact question answering, probably you can effectively use only 10 to 20% of your input context, not the whole context. Yeah, what will happen if you need 2 facts to answer your question? Yeah, very sad news. Yeah, you see that you have even worse results. So, like only, even without any background noise, only GPT-4 higher than 85. So if you have 3 facts, for 3 facts, you see that it's in these settings, any LLM is useless, even without adding any background text, actually. Very strange. So you see the contradiction. We have very smart LLMs, but they are not able to solve these very simple tasks. But can we solve it? Yeah, sure. If we trade off universality, and if we will trade to create and train architecture which is task-specific, we can get much better quality. And here what we did, we take a transformer and added recurrent memory to it with a very simple way without changing any underlying architecture, just by introducing specific memory tokens to vocabulary and fine-tune this architecture as a recurrent neural network. We were able to achieve much better results. For example, here you can see if we take 10 million tokens and compare with a RAG on 10 million tokens will give you 14%, and our approach gives you on 10 million tokens 76% accuracy of giving answer on this data set. One supporting fact question answering. If we take, and this 10 million, it's like a full Encyclopedia Britannica. If one book is about like 100 tokens, then you can get 99% accuracy with recurrent memory transformer, and you have like a 60% or 70% with RAG, and 20% with GPT-4. But if you have just like 6-10 pages, GPT-4 is great, and with a specialized model you have also 100% accuracy, but here you have only 137 million parameters. It's just like you take a GPT-2 and add recurrent memory to it, and for this specific task, if you fine-tune on it, it will get much better results. Yeah, but we can go even further. We can add not only this recurrent memory, but also combine this transformer architecture with a linear attention memory blocks, and then we have associative recurrent memory transformer, which is even better than recurrent memory. It can have an 80% accuracy on 50 million tokens for these tasks. And on 10 million, it's still pretty good for 2 question, for example, 2 facts question answering. In many cases better than like conventional linear transformers, like all these state space models like Mamba and stuff like that. So here the conclusion is, if you have specialized models or specialized architecture, probably you can solve this long context problem. So is AGI around the corner? I don't think so. And probably, if we will find proper way to fine-tune LLM or some other kind of model, or it might be multimodal multimodal model like video, images, financial transactions, texts, all of that together, and we find a proper way in objective to train our model, not only memorize stuff, but also to try to abstract some patterns, some rules governing generation of data. Probably we can reach AGI in the real future. I don't know, actually, correct answer to this question, but we have some parts of our final solution covered, but still many other things like good exploration, continual learning, novelty detections like self-modeling, and planning, still open problems for current LLM models. So just quick takeaways from my talk. So in recent years, LLMs create expectations of really true AI, and they are really good at imitating language and approximate problem solving. But certainly right now, if you use them, you should either apply them where a cost of error is low. But if the cost of an error is high, then you need to add some external verification, which will verify answer of your system. And as we've seen, everyone is very excited about autonomous agents, but it seems that they are not mature enough, and main limitations that they fail to master generation and application of abstract rules, and not very good at reasoning and planning due to probabilistic nature of generation. But probably if we will have long context with plan verification and find good objective to train model to abstract rules, then we can significantly improve agents' performance and make them really useful. And another lesson is that small models which are trained or fine-tuned in domain still deliver very, very good value. So thank you very much for your attention. Questions, please.
Thank you very much for a very interesting talk. First of all, I want to applaud you for your demonstration how to change your opinion based on new evidence. I think this is what we will have to keep in mind in terms of our conjectures. However, regarding the questions, first of all, you have mentioned that there are combinations of LLMs with knowledge graphs. Can you please elaborate what kind of technology you use for knowledge graphs? Do you rely on W3C knowledge technology stack, RDF, OWL, etc., etc.? And lastly, do you believe that in implementation of knowledge graphs can solve the idiot savant problem that you have mentioned, like that LLM is tying meaning to the particular word it is operating on, and we know that a word is just a symbol, like the structure of the word, the sequence of characters does not actually reflect anything. So can we teach an LLM to create an abstract knowledge graph that will not be tied to particular words? And will that help the LLM to build the world model that you have been referring to?
Okay. Thank you for your questions. So regarding the first question, in our study, it's like research. It's not a production system. So we have not invested a lot of our engineering effort to use RDF or like Wikidata or something like this. We just say like, let's test our idea. If actually with the help of LLM, we just extract this knowledge in some constrained form, so we can set this vocabulary of possible relations which LLM can use and stuff like that. So we can train our model in this way. Will it be useful or not? So this is how we did it. But certainly if you build like a larger scale production system, I think that RDF and Wikidata, for example, this is a good way to go to consider to include in your system and verify your system and like what the system has generated. Basically, this is the idea. As I've said, one of approaches to fight hallucinations and verify models is use knowledge graph, because by definition we believe that that facts which are stored in knowledge graph, they already true in some sense, like by sense of the developer of this knowledge graph. So we can use them for verification. And actually, your next question touches very interesting matter. How we can like what is the definition of truthness for our knowledge graph? So, for example, can LLM build a knowledge graph which is like totally unexplainable, but still very useful for solving the task? In some sense, I think that this is actually happening inside transformer, because if you look at transformer architecture, you will see that it's like it's multiple heads, and every head is a just fully connected graph of relations between elements. And we even had some paper when we probed trained transformer, I think Roberta or Bert, if attention maps can be used to reconstruct semantic relations from Wikidata. And we found that it is possible. So in some sense, transformer by itself builds this knowledge graph inside it, but it's like probabilistic knowledge graph, maybe. So yeah, this is my answer. So I don't see like the strong formal method which can guarantee truthfulness of the graph on one hand, and on the other hand, this knowledge graph is implicitly built by transformers.
Maybe you know that Jan Mikhail claims that the real world model is beyond the text we're having in our planet. So it is not achievable to make an AGI model with text only. And for instance, a cat has no exact language, but it can interact with our world, just jumping on the table and taking the glasses off the table. So what do you think about it?
So I would not agree with Jan Likun. So I think that you can build world model from images, you can build world model from text. It depends on the like how much you can do with this world model. It's like it can allow you to do like different kinds of predictions. For example, if you have a very good world model written in the language of mathematics, like of science, physics, and biology, probably you will be able to predict a lot of stuff about our universe, which we have no idea yet, even without feeding the model with images.
So you mean we should to make some kind of new sophisticated encoding tools, like how to encode some rules of our physics model and just apply it as tokens in the LLMs?
Yeah, it's one approach. I don't know which one will win. Another approach might be you can take a lot of YouTube videos, or you can create a lot of cheap robots and force them to just drop them into the environment, and they will interact with the environment, play with it, and you record all their interactions and train this model. Probably it's another solution. So I don't know which one is much better, but I think that we will see probably soon, because people are investing in this. And as you see, like 3 years ago, 4 years ago, everyone expected that Google soon will release video model, not like LLM. Because it's obvious, if you have LLM and you have YouTube, why not to train video model? And you see right now, we have no such a video model, such good as language model. So we don't know. There are some problems with training.
Okay, thank you very much.